Permafrost is a fascinating and essential component of our planet's geology, defined as ground that remains at or below the freezing point of water, (0°C or 32° F, for at least 2 consecutive years. This frozen ground is found in the coldest regions of the Earth and consists of a mixture of soil, rock, and organic material that has been held in an icy state for millennia. There are several distinct types of permafrost, each characterized by its extent and continuity across the landscape. Continuous permafrost. This type of permafrost is found in the coldest regions, such as the Arctic and parts of Siberia. In these areas, the ground is almost entirely frozen, forming a near-continuous layer that can extend hundreds of meters deep. Continuous permafrost areas are marked by extremely low temperatures and minimal thawing during the summer months. Discontinuous permafrost. As the name suggests, discontinuous permafrost is found in slightly warmer regions where patches of permafrost are interrupted by unfrozen ground. These areas, such as parts of Canada and Alaska, experience more significant seasonal variations in temperature, leading to a fragmented distribution of frozen ground. Sporadic permafrost. Found in even warmer regions, sporadic permafrost exists as small, isolated pockets of frozen ground amidst a landscape that is mostly unfrozen. This type of permafrost is typically found at higher altitudes or in specific microclimates where local conditions allow for freezing. Isolated permafrost. The least extensive type, isolated permafrost occurs in very small patches scattered in otherwise unfrozen areas. These patches are often found in regions where specific environmental factors, such as shaded valleys or high elevation, create conditions conducive to freezing. A global map of permafrost distribution highlights its prevalence in the Northern Hemisphere, particularly in the high latitudes of Siberia, Alaska, Canada, and Greenland. Smaller regions of permafrost can also be found in the Southern Hemisphere, including parts of the Andes Mountains and subantarctic islands. This widespread distribution underscores the global significance of permafrost in our planet's ecosystems and climate systems. Chapter 2. How does permafrost form and change? The formation and persistence of permafrost are influenced by several key environmental factors, including temperature, snow cover, vegetation, and soil type. Understanding these factors provides insight into how permafrost develops and changes over time. Temperature. The primary driver of permafrost formation is temperature. In regions where the average annual temperature remains below freezing, the ground can freeze and remain frozen year-round. These cold conditions are essential for the development of continuous permafrost. Even in regions with higher temperatures, localized cold conditions can still lead to the formation of discontinuous, sporadic, or isolated permafrost. Snow cover. Snow acts as an insulating layer for the ground, affecting the thermal regime of permafrost. In winter, a thick snow cover can insulate the ground from extreme cold temperatures, while in summer, it can protect the ground from direct sunlight and heat. The presence and thickness of snow cover play a critical role in determining the depth and stability of the permafrost. Vegetation. Vegetation, particularly dense ground cover like mosses and lichens, provides additional insulation for permafrost. These plants trap snow and reduce the amount of heat transferred from the air to the ground. In forested regions, tree roots and plant debris can also help maintain the frozen state of the soil by providing shade and insulating the ground. Soil type. The composition and moisture content of the soil influence its ability to freeze and remain frozen. Soils with high moisture content freeze more readily and maintain permafrost more effectively than dry soils. Organic rich soils, such as peat, can also affect permafrost dynamics due to their insulating properties and the heat generated by decomposing plant matter. Permafrost is not a static entity. It undergoes seasonal and long-term changes. The top layer of permafrost, known as the active layer, thaws during the summer and refreezes in the winter. The thickness of the active layer varies depending on the local climate and environmental conditions. Over time, the depth of the permafrost can increase or decrease based on long-term climatic trends and local environmental changes. A cross-section diagram of permafrost illustrates the active layer on top, which experiences annual thawing and freezing cycles, and the deeper, more stable permafrost layer beneath. This deeper layer can extend hundreds of meters into the ground, remaining frozen throughout the year and providing a significant carbon sink and a stable foundation for ecosystems and human infrastructure. Chapter 3. Why is permafrost important? Permafrost plays a crucial role in the global climate system and supports unique ecosystems, making it an essential component of our planet's environmental health. Climate system. One of the most significant functions of permafrost is its role as a carbon sink. Permafrost regions store vast amounts of organic carbon, accumulated from plant and animal matter over thousands of years. This carbon is locked in the frozen ground, preventing it from decomposing and releasing greenhouse gases like carbon dioxide and methane into the atmosphere. By trapping these gases, permafrost helps regulate the Earth's climate and mitigate global warming. Ecological importance. Permafrost regions support unique ecosystems and habitats that are adapted to cold environments. These ecosystems include tundra landscapes, boreal forests, and wetlands, each hosting a variety of cold-adapted species such as reindeer, Arctic foxes, and migratory birds. The thawing of permafrost can disrupt these ecosystems, leading to the loss of habitat, changes in vegetation, and declines in biodiversity. The delicate balance of these ecosystems is intricately linked to the stability of permafrost. Infrastructure challenges. Permafrost presents significant challenges for infrastructure development. Buildings, roads, pipelines, and other structures built on permafrost are at risk of damage from thawing ground. As permafrost thaws, it loses its structural integrity, leading to ground subsidence and instability. This can cause severe damage to infrastructure, posing economic and safety risks. Engineers must design buildings and infrastructure with these challenges in mind, often using specialized foundations and insulation techniques to prevent damage. This includes methods like elevating buildings on piles, using thermosiphons to keep the ground frozen, and insulating foundations to reduce heat transfer. In summary, permafrost is vital for maintaining global climate stability, supporting unique ecosystems, and posing challenges for human infrastructure. Its significance extends beyond its immediate environment, affecting global processes and human activities in profound ways. Chapter 4. What is happening to permafrost due to climate change? Climate change is having a profound impact on permafrost, with rising global temperatures causing permafrost to thaw at an alarming rate. This thawing has several significant and far-reaching consequences. Thawing rates. The rate at which permafrost thaws varies depending on the region and local conditions. However, the overall trend is clear. As global temperatures rise, more permafrost is thawing, and the active layer, the top layer of soil that thaws and refreezes annually, is becoming thicker. This process is particularly pronounced in the Arctic, where temperatures are rising at more than twice the global average rate. Consequences of thaw. The thawing of permafrost leads to a series of interconnected consequences. Greenhouse gas release. Thawing permafrost releases carbon dioxide and methane, potent greenhouse gases, into the atmosphere. These gases were previously trapped in the frozen ground, and their release contributes to global warming. The decomposition of organic matter in thawed permafrost further accelerates this process, creating a feedback loop that exacerbates climate change. Land subsidence. As permafrost thaws, the ground loses its structural integrity, leading to land subsidence, where the ground sinks and collapses. This subsidence can cause severe damage to buildings, roads, and other infrastructure, leading to costly repairs and increased risk for communities living in permafrost regions. Coastal erosion. In coastal areas, thawing permafrost destabilizes the ground, making it more susceptible to erosion from waves and storms. This can lead to the loss of coastal land, impacting local communities, ecosystems, and infrastructure. The increased erosion also releases additional organic carbon into the ocean, further contributing to greenhouse gas emissions. Damage to infrastructure. The thawing of permafrost poses significant challenges for infrastructure development and maintenance. Buildings, roads, pipelines, and other structures built on permafrost are at risk of damage from the ground shifting and collapsing. This can lead to economic losses, safety hazards, and the need for costly adaptations and repairs. Chapter 5. The permafrost carbon feedback loop. The permafrost carbon feedback loop is a critical concept in understanding the impact of permafrost thaw on climate change. Greenhouse gas emissions. As permafrost thaws, It releases carbon dioxide and methane into the atmosphere. These greenhouse gases were previously trapped in the frozen ground and are now contributing to global warming. Feedback loop. The release of greenhouse gases from thawing permafrost creates a feedback loop. As more greenhouse gases enter the atmosphere, they cause further warming, which in turn leads to more permafrost thaw. This cycle accelerates climate change, creating a situation that is difficult to reverse. Illustrating this feedback loop shows how interconnected and potentially devastating the process can be. It emphasizes the urgency of addressing permafrost thaw as a significant factor in mitigating climate change. Chapter 6: Engineering Solutions for Permafrost Thaw. Innovative engineering solutions are being developed to address the challenges posed by permafrost thaw. Thermosiphons. One such technology is the use of thermosiphons, which are passive cooling devices that help keep the ground frozen. Thermosiphons extract heat from the ground and dissipate it into the air, stabilizing the permafrost and preventing thawing. Ground insulation. Ground insulation is another method used to protect permafrost. By adding layers of insulating material, heat transfer to the permafrost is reduced, helping to maintain its frozen state. Improved foundation designs. Engineers are developing improved foundation designs for buildings and infrastructure. These designs accommodate the potential for ground movement, reducing the risk of damage from thawing permafrost. For example, buildings can be constructed on piles driven deep into the ground, below the thawing layer, providing stability even as the upper layers of permafrost change. Chapter 7: What can we do about permafrost thaw? Addressing permafrost thaw requires a multifaceted approach. Reducing greenhouse gas emissions. Reducing greenhouse gas emissions is crucial to slow down the warming that causes permafrost to thaw. International agreements and policies aimed at reducing carbon emissions play a vital role in this effort. Adaptation strategies. Adaptation strategies are essential for communities and infrastructure built on permafrost. These strategies include relocating vulnerable structures, designing buildings to withstand ground movement, and implementing local cooling techniques. Ongoing research and monitoring. Ongoing research and monitoring efforts are critical to understanding and addressing permafrost thaw. Scientists are studying permafrost dynamics, developing predictive models, and exploring new technologies to mitigate the impacts of thawing. Collaborative efforts among governments, researchers, and communities are essential to develop effective solutions and policies. In conclusion, permafrost is a vital component of the Earth's cryosphere, playing a significant role in the global climate system and supporting unique ecosystems. However, climate change is causing permafrost to thaw at an alarming rate, leading to the release of greenhouse gases, land subsidence, and damage to infrastructure. Understanding the importance of permafrost and addressing its thaw through innovative engineering solutions and emissions reduction is crucial in the fight against climate change.